we can.
Okay, thank you. So thank you for the introduction and the warm words. I'm going to talk about risk and robustness in RL. This is work with many people, so I will not mention them during the talk. And really, I know this is an applied probability audience, so I'll tell you a little bit about RL. So RL really is about sequential decision maker. Here we see Tetris. In Tetris, as I'm sure you've all wasted much time during your youth. There are bricks falling, and you need to clear lines. Whatever decision you're going to make, meaning whatever bricks are going to fall, are going to affect what you can do sequentially. Perhaps the most successful application of RL is in the stock market. So this is an American put option. American put option has a contract that gives its owner the right to sell stock at a strike price K. So if the price is above K, the option is valuable. If it's below K, there is no value to the option. And there are many questions in American put options, such as when to execute, but also, and perhaps more importantly, how to value the option itself. Yet another example. This is a very simple pinball domain. So in pinball domain, there is a blue ball and a red dot, and your objective is to get the blue ball to the red dot. And you can, in this case, there are two paths you can choose. It's a pinball, so everything shakes all the time. So it's not such an easy control task. You could take the longest path, which is safer but will take longer, or you can take the shorter path, but then you might hit the wall. If you hit the wall, then you can get reflected back. So you need to decide if you're going to take the safe route or the longest route. And there are, of course, many pinball problems. So I'm going to talk today about the classical RL model. So we have a macro decision process, which we call an MDP. There is a controlling agent. There is a controlling environment or a controlled entity. The agent observes some indication of the state and gets a reinforcement signal, the reward. And as a result, the agent sort of figures out what to do and chooses an action that is going to affect the controlled entity. So this is a classical model. We have a state space S, a transition probability P, a reward function R, and a state space A. And it's very common in RL. The state space and the action space are known. This is part of the problem. But the transitions and the rewards are not known. So we don't know the dynamics of the system, and we don't know what you're going to get. And the classical objective, which we'll discuss throughout most of this talk, is the expected cumulative discounted return. So basically, you're trying to find a policy that would give you the maximal expected return. And I just want to mention this famous quote by Box. This is, of course, just a model. We don't pretend reality to be like that. This is just a model of reality. Okay, so what happened in the last 5 years or so? Basically, we have many algorithms, and you see the algorithm. This is a taxonomy of the algorithms. I'm not going to get into it. There are broadly 4 families of algorithms. So we have many algorithms, but we have relatively few real-world successes. The most recent one was, I think, DeepMind's ability to control balloons floating through the atmosphere, but still we don't see many successes. And the question is why? Why don't we see many successes? And what should we do to make the RL work a little bit better in the real world? So let me start with reductionist fallacy. So those are 3 sentences I think everybody would agree with. So only smart people can play chess, for example, very well. I'm sure you agree that to be a good chess player, you need to be very smart. Actually, you also agree that almost everybody can tell a joke. And then, well, you also agree with that computers are really good at chess. I mean, definitely better than humans. So the reductionist fallacy that because telling jokes is easy for humans, and computers are very smart in the sense that they play chess, then the logical conclusion must be that computer can easily tell a joke. I know how many jokes you've heard computers telling, but it's not very funny. So there is this notion that when we think about problems, we're making reductionist fallacies. and we pretend that some problems are much easier than they really are. This alludes to a book by Shie, who was the MIT Media Lab director, and basically we offer simplifying problems that are easy for us. We pretend that they're easy for computers, and that's something that we need to combat and having a clearer vision in our mind. This is not really the case. So, and there are people that are trying to do AGI, so the Terminator or Agent Smith or Commander Data, whatever you would think, but this is really what most computers can do. So with the exception of the latest Boston Dynamics video, which I'm sure everybody here have seen, of robots dancing, this took about 3 months to choreograph. So the way we build robots today is very far from what we think or what we like to be. So we'd like it to be. So intelligence is still very, very far, and definitely we're very far from AGI. And in my research, I'm trying to try and solve intelligence, so try to get intelligence to work a little bit better. I want just to mention that when you think about RL problems, and there are really 3 types of problems. There are static problems. So in the example here of the Pac-Man, imagine that Pac-Man has everything else is stable, nothing moves. So the problem is really a planning problem. Just get as many fruits as possible and don't touch the ghost. This is a problem when I don't care about other agents. So they don't exist as far as I'm concerned. In the case of, if you think about self-driving car, then this is like I'm driving in the road, but there is no one there. So this is not a very difficult problem when everybody else is static. And then there are dynamic problems. So this is the case where the ghosts don't see Pac-Man, and everything is moving, but still it's not moving very quickly, and does not relate to what I'm doing in particular. So dynamic problems are a little bit more difficult because there are other agents that are moving around, but they don't react directly in response to what you're doing. But the most interesting aspect of learning in the real world is the counterfactual aspect. So in the case of Pac-Man, if anyone ever played Pac-Man here, I'm sure most people did, the ghosts do react to Pac-Man. So they sort of know what it's doing and they try to catch it when they can, and when Pac-Man eats a fruit, then Pac-Man is trying to eat them. Or in the case of driving, when I'm driving on the road, other cars are going to react to what I do. So basically, there are those 3 types of RL problems are really what is interesting. We're pretty good at static problems. We're not that bad at dynamic problems, and we're pretty clueless in counterfactual problems. So the way we model interaction between agents, whether they're computer agents or human and computer, is just not there yet. We don't have the theory. We don't have the tools to use it. And just so I've worked in the last 3 years on self-driving cars. Just to mention that an RL problem, it's a very complex problem. I don't know what is in my reward. I don't know what I observe, and I also it's not even clear what I can do. The reason that it's not clear what I can do is that ultimately my control is what I do with the steering wheel, gas and brake. This is of course pretty difficult to consider because humans don't think in terms of I'm going to press the brake for 1.35 seconds and then I'm going to tilt the steering wheel by 30 degrees per second for 0.8 seconds. So humans think about actions in a much higher level. They use a much more complex abstraction, and it's not clear that how to even formulate driving a car as an RL problem. But that's a different topic for a different talk.
Shai, we have a number of questions. Would you like to take them now?
I think we should wait because currently I'm just giving an overview, and then I want to dive into one particular topic which I think is very important, and then we can take it. I think then. Okay. So what I'm advocating that we should think about not artificial intelligence, which is perhaps an overly ambitious goal, but rather something which is a little bit less ambitious, which I call extended intelligence. So basically, how you design a system that would work with other systems, human or not, where the RL-based system knows that it's going to be interacting with someone else. In the case of a self-driving car, so it's not a completely fully autonomous self-driving car, but rather a system that knows that it operates with a human in the loop, and the human is going to tell it what to do, take the steering wheel occasionally, and so forth. And there are 5 principles of extended intelligence, and that's how I value research in the field. They're written here. Awareness means that you know how well you're doing. Accountability means that you can explain why you did what you did, maybe in words, maybe by showing calculation. Adaptivity means that you function not only in the condition that you were trained for, but in somewhat different conditions. I think those are undebatable. The most important one, though, is the next one, which is life cycle consciousness. Basically, debugging an RL system is virtually impossible. So trying to understand why an RL system doesn't work is extremely difficult. And currently, I think this is the main impediment in wide-scale application of RL. And then, last but not least, we need to be able to scale with resources, more compute, more data. We want to have a better policy. So those are the 5 principles, and this is how I evaluate research in RL according to the contribution to those five principles. What I'm going to do in the rest of this talk is I'm going to talk about risk sensitivity and robustness. So I'm going to talk about a particular aspect of the broader scheme of things that's going to focus on adaptivity, to some extent accountability, and scalability. We're not going to talk about life cycle consciousness, even though it's very important, and I really focus about adaptivity and scalability. So we want to adapt situations that are we're not trained with. So before I move to the next to the main part of the talk, now would be a good time to take some questions. Sandeep, I can't hear you.
Yeah, so let me read some questions. So Devavrat Dubashi was asking that Boston Dynamics robots don't use RL or ML or any ML, right?
Yes, this is correct. They use model predictive control. And as far as I know, unless I talked to them within December, they don't use any RL.
So he's also asking counterfactual here means multi-agent. Is that right?
Counterfactual meaning means multi-agent, but not necessarily so, but also there might be objects in the environment that are not fully operating agents, but rather they react to you. So they don't have to be selfish agents on their own.
All right.
All right. So let me continue then with the main aspect of this talk. So why should you be risk sensitive? So this is the example, the pinball example we had before. There is a blue ball that you control with the objective of getting to the red target, and you have 2 options. You can go through the longer and safer route, or through the shorter and more risky route. Just to give you an example, so suppose you want to get to the airport, and the question is which one should you choose? And when you look at the lower route, the riskier one on expectation, it looks better, but it still is heavier. So if your flight is around here, your flight time, you're probably going to take the longer and safer route because it will get you there with high probability. So the point of the exercise, it really depends on your objective. So what we're saying here is that if you're going to be risk sensitive, as in you're going to try and minimize not the expected time, but rather some risk measure, then it's going to lead to robust policies. So when you talk about uncertainty, what are the type of uncertainties that we have in mind? So there are 3 types of uncertainty that we consider. The first one, which we'll address today, is what's known as parameter uncertainty. So basically, I'm not sure what are the model parameters, maybe because I didn't sample enough, maybe because things are changing, but I want to find the best policy under the worst possible parameters in some uncertainty set of the expected discounted return. The second type of uncertainty is what we call inherent uncertainty. That just because there is randomness in the process itself, we know the process, but there is some inherent randomness. For example, if I offer to you guys to play the following game with probability half you win $1, probability half you lose $1, most of you guys will eagerly play it for fun. But then if I'm going to make the stakes 1,000 or 1 million larger, then I think for most of you this will become much less of a fun game, even though in expectations the two policies are the same. So policy 2 is of course, if you're risk averse, and policy 2 is something you're not going to choose, and if you're risk seeking, then maybe policy 2 would be a good idea. So the way we model it is we want to find the policies that maximizes some risk measure. In this case, you can think about it like what's known as variance adjusted expectation, but there are many other risk measures you can consider. And I just mentioned that humans tend often to be risk aware, either risk seeking or risk sensitive, but risk has been shown time and time again to be an important factor in the decisions that humans are making. And then there is the most interesting type of uncertainty, which we'll just touch upon today. And that's what's known as model uncertainty. So in model uncertainty, the model itself is not known. So you're not sure exactly what even the class of the model is. And you define your policy not in terms of in terms of your policy, basically you want to maximize the return, but under the worst possible model. So it's not just parameters that are you don't know. The model itself, maybe it's a Markov model, maybe it's a non-Markov model. You don't really know. And then you want to be able to address a model mismatch directly. Okay, so risk sensitivity is important because it's important in many applications where failure is expensive. And now we all also mentioned that in almost all problems of interest, the model is not really known. And as I said before, we want scalability. So we want algorithms that would work better with more data. We want adaptivity, and we want accountability. So we want to be able to, at least to some sense, explain why we chose the policy that we did. And a good explanation can be, I chose a particular policy because while this is not the optimal policy for the current model, I was unable to tell whether it's model A or model B, and it's good against the worst of the two. So that's a reasonable way to produce accountability. Okay, so before we go any further, I just want to mention something about computational complexity. I had a paper with John Stiglitz about 7 years ago. Basically, in this paper and quite a few follow-ups, all those problems is difficult. So from now on, we don't discuss NP hardness. All of the problems are difficult. So we'll forget about trying to find is a solution. In very few cases, there is a miracle, but most often, the problems that we're trying to solve are very large. So let's ignore complexity for the rest of the talk today. Okay, so I'll start with talking about a very particular problem. It's called robust MDPs, where you're using function approximation. And let me explain what are robust MDPs. So the problem is a planning problem. So everything is known. There is no learning involved, or learning, if any learning happened, it happened before. And the transitions are uncertain because maybe we sample data and we have confidence intervals around them. Maybe we have a simulator that we're using, or maybe the dynamics themselves change with time. So we're not sure what are the transitions. So in a classical MDP, you have say state S0 here, and you have the conditional transition to S1, S2, and S3 that sums up to 1. In an MDP which has uncertainty in it, in a robust MDP, we're not exactly sure what is the conditional transition from S0 to S1, but rather there is an interval around it, or we're not exactly sure what's the conditional transition from S0 to S2. There is an interval here around it representing the level of uncertainty. Okay, so just to be a little bit more precise, the state actions in the world are the same as the standard model. The transitions now, all that we know about them, that they belong to some uncertainty set, which is a convex uncertainty set, which we have a precise definition of. And we're looking for a policy pi that would maximize the worst case objective. So it's a soup over policies, infimum over all parameters. So this is a parameter uncertainty of the expected discounted return. And if you wish, you can think about it as a game that there are two players. One player chooses a policy, and then nature plays the worst possible model against this policy. So it's a game against nature kind of thing. Okay, so how do you solve such problems? So for a fixed policy, you can show that this is what you're looking for is you're looking for the policy for a fixed policy pi. Your value function or robust value function is a worst case overall possible model of the discounted return. And the way to think about it is that I choose pi, and then nature is going to maliciously find the worst case model against me. So here, from all the possible transition, it will choose the conditional transition that is absolutely worst for me. And then maybe I'm going to move to state F3, and then nature again will choose the worst possible transition from it, and so forth and so forth. So the sampling process involves me choosing a state and choosing an action, and then nature choosing the worst possible model against me, and so forth until the process continues. So you can show that for a fixed policy, there is a nonlinear, but nevertheless a not too difficult Bellman equation. This is a fixed point equation for trying to solve for v of pi. So the value of pi is equals the return plus discount factors times this infimum over all transition probability of the policy. So this is the robust Bellman equation, and you can even solve it if you're optimizing over pi. And this was solved about 15 years ago using policy iteration or value iteration for small problems. For large problems, of course, we cannot enumerate the state space. The state space is too large for us to enumerate. So we need to find another approach to solve it. This is a so-called curse of dimensionality. Okay, so let's take a baby step. So what do we do when you have a large state space? So the classical thing to do, the simplest one, is to build an approximation. This is known as the approximate value function. So we try to approximate the value function as a multiple of some feature-dependent set. So this is a feature-dependent vector, predefined, and a vector W, which we're trying to optimize. So the idea is that we want to find W such that V tilde of pi, the approximation, is close to the actual true value. So how do we do that for a standard non-robust MDP? We take the value V pi of S, and we write it as the expectation. We want to approximate it as a linear approximation at the function of W. So we're actually going to sample many trajectories. So I'm going to sample, say, 100 million, maybe 1,000, 10,000, a million trajectories. And then I'm going to sample and regress with respect to W. Because I have an estimation from the expectation. I have a phi of S, which is fixed and known. And so all I need to do is to regress for W. So this looks easy enough. But then the issue is what can I do for the robust problem? So for a robust problem, even for a fixed policy pi, then I have this infimum here. But I don't know how to sample trajectories from the worst case model, because in the dynamics that we had before, I choose a main policy, and then the adversary chooses the worst possible policy against me. But in this game against nature, the adversary has to solve the game. So I don't know how to sample trajectory from the worst case model. That's sort of the crux of the matter, that this worst case model is unknown to the adversary or to me. So what's the idea? So the idea is really to bootstrap. And recall the Bellman equation, which is written here. So what are we going to do? We're going to start with initial weights and sample n samples from the states. And then at every iterate, we're going to pretend that our previous estimation is good. And if our previous estimation is good, so if the value function can be represented as a multiplicator as WK times the previous estimate. So it's this is my previous estimate of the value function. Then if I pretend this to be the case, then I can still have solve this infimum now, because the infimum involves what I know, but I pretend that my estimate is good enough. So the trick is that I start from some W0, and then I solve WK plus 1, given that I trust my estimate WK, and I do it essentially up until convergence. So this is a trick whose purpose is to circumvent not knowing the model precisely. So this is the algorithm. It's essentially a very simple algorithm. You need to solve a nonlinear, but still not a very difficult, robust optimization problem at every stage. And the guarantee that you can get is that you get convergence and you get error bounds. The error bounds are in terms of how good your approximation is, because if your approximation initially, if your approximation is not good original, then there is not much you can do. And if it's good, then essentially you're all set. So if you have a good approximation, maybe because phi is very large, or because you have some insight in the problem, you can actually prove error bounds and convergence, and then you can go into a deep architecture, derive a Q-learning algorithm, and so forth. So essentially, once you let the bootstrap work for you, then it allows you to solve robust problems.
Shie, there are a number of comments and questions. Would you like to take them?
Yes, now would be a good time, actually.
Sure. So there's a question by Zaiwai Chen. How do you carry out the algorithm when the transition probabilities are not known?
This is a planning problem. You need to assume that the transition probabilities are known. If they're not known, you can do a Q-learning type approach, which is going to add another layer of complexity. But in principle, this is for a planning problem.
Okay. Now, there are a number of comments from your earlier slides. I'll just go through them quickly. So Shalabet said that there's another formulation of risk-sensitive models, those with exponentiated cost structures. So yes. Is there a connection of such formulations with this one?
Not with this one, but with the next one we're going to address, definitely there is a connection there.
Devavrat Dubashi then said chance constraints are also used to model risk-sensitive constraints. I
didn't hear that.
Chance constraints.
Yeah, so we'll discuss that shortly.
And I think there's one question from Rahul. How do these models account for random delays before current action impacts performance of the system?
The short answer is that they don't. Right. This is a very important topic of delay feedback, but it's not addressed by it. Very important and very actually current research topic.
Okay, Alka Yadav is asking that can we use other algorithm too in place of bootstrap?
So I don't think so. I think that at least for this particular problems, I was unable to come up with any other algorithm. If there is another algorithm, I'd be excited to hear about.
Okay. Shala Bhatnagar is saying output of the algorithm would lie outside the subspace, wouldn't it?
Yes, it would, and then there is also a projection step which I ignored for the sake of brevity, but yes, of course, Charles is right.
Devavrat is saying, how do you get good representations for a state from deep networks?
That's the million-dollar question. This work assumes that good representations are given. I think it's a topic of a whole new I would say research endeavor on finding good representations.
Okay, a couple of more questions. So Shashwat Mishra is saying, isn't the algorithm sensitive to the initial point?
it's sensitive only in terms of convergence rates. If you can show, in fact, that if you start in a good place, then you'll get there faster, get faster to convergence. But it's only sensitive in the sense of rates.
Okay. All right. So last question from Ikra Atlaf. Does sampling method affect end result?
Yes. So the sampling method that affect the end result, and in fact, you can show that you can speed up convergence by a large margin if you sample things in the interesting regions. That's again, I mean, the topic of how to sample for planning is quite interesting and also a very current research topic.
One more question now. This is convergence of a non-linear optimization problem, right?
Right.
The local or global optimization.
So you converge to a low in the particular case of a linear function approximation, not in the deep case, you converge to actually a global optimum, but it's not necessarily the global optimum that you want, because you may not be able to represent the value function because you're doing approximations. So you are getting converged to something that is global. The convergence is not local in the sense it's not a gradient-based algorithm. However, you are converged to a place which is a global optimum. Okay, so let me just show you a result which is curious and interesting, and in fact I don't know how to explain it. So here is the American put option we had before. Basically, the question is when to execute, and you need to do that to evaluate the option. Remember that when the price is more than K, I can make money. When the price is below K, it's worth 0. So I want to know when to execute. And you can formulate it as an MDP. There are many formulations, and you can estimate the price transition from local data. And of course, because the model or the stock market today, or 2 days ago, it may be the same, but maybe 3 years ago, it was completely different. So the stock market changes and everything changes. So we don't really believe that we have enough data. Okay, so let me show you an experiment that was done. It was done with everything is in simulation. So no real data was used. So we know exactly what happened. So the true model is a mean reverting transition that depends on price. So there is a particular trend, and the sort of the price of the stock wants to go back to this trend. So this is there are many such models. So this is a particular mean reverting model. But to estimate the model itself, we used a constant transition model. So we used a much simpler model, not mean reverting, but rather a simple constant transitions. So here we're looking at the model class that we're trying to use is different. It's just not, we're not solving the right model class. We're trying to solve for a simpler, overly simplistic model class. And what we see here, this is A, and we see the probability that the return is more than A. So this is, remember that because whenever we go below the execution price, we cut the process, then we're always going to make more, at least 0. So, and this is the probability of making more than $8 per trade. So, and what we see here, this is the nominal policy in blue. So this is basically estimate from data, use your estimation, and see what gives in testing. And in red, we see the robust approach. So the robust approach dominates the nominal approach, and remember that it doesn't make a lot of money, but it makes money more consistently. So what we see here in this experiment, and there are other experiments like that, so that when you choose a robust policy, you get robustness not just for not having the right transition distribution, but also to not having the right model class. And that's a very interesting property that, while I have an intuitive explanation, I don't have a theoretical guarantee here. And if anyone wants to have an idea how to do it, I'll be happy to, if they shoot me an email because this is, I think, a very interesting, a very weird phenomena, actually. Okay, so let's move to the second part of today's talk. I'm going to talk about risk-sensitive policy gradients, and especially about conditional value at risk. So let's just remind ourselves what the definition of the CVaR. So if you have a random variable x and alpha is a quantile, then the alpha CVaR is a condition expectation, given that you are in the low alpha quantile. So condition that if say alpha is 5%, then condition that you're in the 5% worst event, then this is how much you believe you're going to get. Also known as expected shortfall by our economist friends. And this is, of course, this risk criterion amplifies rare disastrous events. So estimation is trivial, right? Because to estimate the mean, you just take the empirical mean. To estimate the CVaR, you just take the alpha and worst samples and average them. So estimation is trivial as long as alpha is not really small. So if it's not something that is order of magnitude of your data, as long as it's not really small, estimation should not. There is no real problem. So think about alpha for the duration of the stock as 5%. So it's not really 1 to the power of minus 6, 10 to the power of minus 6. It's a reasonable number. Okay, so what people often do in RL is that they encode the policy by parameters, for example, deep network parameters, and then those parameters are going to define the control policy. The control policy defines the stochastic, affect the stochastic systems, and the payoff function. So in the standard objective, you want to maximize over your policy, those are the parameters of the policy, of the expected return. And in the risk objective, you just replace the expectation with some risk measure, for example, the conditional value at risk. So the framework is exactly the same. Or maybe something which is a little bit more interesting, like you want to maximize the expectation, but you want your conditional value at risk to be more than something, or different combinations of that. So what happened in the previous work, what people mostly from finance looked at the situation where they only affect the payoff function, and they do not affect the system itself. So the stochastic system itself, because the current common belief is that if there is a market and you only affect your own portfolio, you're a small fish and you don't affect everything that is happening to the system itself. But we being engineers, we are also going to affect the stochastic system. So we think about the conditional value at risk or other risk measures are measures that affect everything around us. Okay, so what we do, basically, we're going to show how to estimate the gradient of the conditional value at risk. The gradient here is with respect to the policy parameters, and how to use a sampling-based estimator to solve the problem, and then the update of the policy itself, that's sort of standard stochastic gradient descent type of approach. So let's talk about gradient estimation. So this is known as a likelihood ratio method, reinvented in the RL circles as a policy gradient. The idea is really simple. You want to estimate the expectation of a random variable x. We just rewrite it and then do some manipulations. This equals the expectation of the gradient of fx over fx times x, and this can be approximated as taking the sum of the gradient of the log of the likelihood of each xi times xi. So this is really elementary manipulations. Under some there are some user buyer's remorse here that you need to be a little bit careful, but all in all, this is a simple algebra, and what you get is that you can estimate the gradient fairly efficiently as the sum of the log of the likelihood of your sample. Okay. So so this is for expectation. So maybe if you want to do the same for a CVaR, maybe we can take the gradient to look at alpha and worst samples, and then just sum those guys up. So exactly the same expression that we had before. But this does not work. And the reason that it does not work is because of Leibniz integral law. This is, I remind you, calculus 1 or 201. And just to remind you what it means, if you want to integrate from minus infinity to q, and once you do the differentiation, you need to take into account the fact that the q itself is going to change. So Leibniz integral law tells us that we also need to take into effect the change in the quantile itself once we change the parameters according to which we derive. And this is basically written here. So you need to, when you integrate when you look at the grant of the integral, you need to take here this minus infinity to q, and then you need to have the gradient of q times the likelihood of it. So there is a correction term you need to take into account that comes essentially from a very classical result. So what is the result then? Once you factor everything, then you get that the gradient of the CVaR is the expectation of the log likelihood ratio. But here you need to deduct the q, the actual quantile of the parameters that you have. So the understanding is here that everything that we see here has an additional subscript of theta. So the parameter that we're trying to that we derive with respect to appear in every term here, every term. But of course, we don't know the quantile because it's hard to compute. So instead, we can take the empirical quantile. And now our formula is quite simple. Take the alpha and worst samples, but replace q with the empirical q. And this is going to introduce a bias. So this is going to mean that our estimation of the bias is going to be our estimation of the quantile is going to be biased, and therefore of the gradient. But still, the algorithm is as following. So you draw n IID samples, you estimate the empirical quantile, sort them, select the worst elements, and estimate the CVaR. So the algorithm is essentially the same algorithm that we know for estimating the mean with a few small modifications. So we just need to modify it accordingly. And then if you do that, then basically everything falls through. You get a gradient algorithm. But I want to show an example to give you an intuition of what is going on. So this is a Tetris example that we had before, and we compare two algorithms. We compare this CVaR optimization for, I don't remember what alpha is, probably 5% or something like that, and the standard algorithm. And here we see the histogram. So the standard policy gradient had an average reward of, it is in red, it had an average reward of 451 as opposed to 414 for the CVaR optimization. So you see that it's, on average, it's better. But you also see, just from observing, that you get a lot of concentration of the CVaR optimization around from, say, 400 to 450. So obviously, when you optimize for the average reward, you get better results on the average reward. But let's see what happens when you look even at the quantiles. So the quantile of the CVaR is lower than the quantile of the average reward. Now, at this point, you should be concerned because I told you that I'm optimizing the conditional value at risk. But the quantile itself is not the same as the conditional value at risk. And let's see the picture. So here I zoomed over the really low scores. So this is the score that are really low. And we see that in red, the histogram of the standard policy grant as opposed to blue, the CVaR optimization. And indeed, what we can see is that what CVaR is buying you, it's buying you resilience in the very low values. So basically, if this is the point where you would be embarrassed that you didn't manage to play Tetris even remotely well, this is not going to happen when you do CVaR optimization. When you do mean optimization, it may happen to you. So my claim is that when you do CVaR optimization, you can get results which are really good. across the board. However, on average, there is no reason to believe you're going to get a good result. So,
Shai, one question was there. So Devavrat was wondering, you're using this likelihood ratio method, and it's known to have high variance. So is that something you see, and do you consider alternate methods?
Yeah, so this is true. Policy gradient methods are known to have, in practice, high variance. For this particular problems, the variance is small because this is a fairly small, easily explainable problems. I think in the last 3 years, there have been quite a bit of progress in making those problems less and less noisy, and I think those algorithms are pretty good. So, in fact, you can combine CVaR with things like SAC, soft autocritic, or things like the TRPO, proximal optimization of different types. So while true, I think at this point this is not such a big concern because we know how to reduce variance. Plus, we have pretty big computers.
Okay. Vika just wanted to clarification. So she says, could you please explain the average reward here again? What does it mean?
Yeah, so there is a reward function, which is, I'm not going to get into it, but basically every brick that you don't fail, you get a point, and whenever you clear a line in the Tetris, then you get some bonus. So average reward means that you look at all trajectories, and for all trajectories are the same. So let's suppose you're going to run 1 million trajectories. You're going to take the middle numbers, you're going to sum them up, and this is going to be, or take the average, and this is going to be average reward. The CVaR, on the other hand, you take the million trajectories, you look at the score that you got per trajectories, let's say 5%, you take the million trajectory, take the lowest 5%, and you just average them. It represents an attitude to risk, if you wish, and especially when the numbers are not very low, this represents an event which is likely to happen, as opposed to something that is unlikely to happen and you just want to protect against. By the way, how am I doing on time?
I mean, I guess we are kind of nearing the end. So, but you can go for another 5 minutes.
Okay, so I'm going to skip other risk measures. They also work, and I want to give you a taste of a result that we have. So initially, I said, risk awareness and robust policies is kind of the same, and I waved my hands. And at this point, you say, well, this guy is waving his hands. Why should we care? But there is a result that we can prove, which is a special case of a much more general result, and that's the following. So what we're going to show now, or argue at least, is that when you solve for conditional value at risk, it's exactly the same at the particular robust optimization problem. So CVaR optimality and robust optimality are exactly the same. And let me be here a little bit more precise. So you can look at what we call multiplicative perturbation. So this is the case when I have a nominal value P, and I look at all the transitions where the nominal value is multiplied by some delta, and there is a budget for all the delta. So delta 1 times delta 2, all that, the product is less than some eta. So basically, this entangles the transitions from different states. So the transitions at, say, the conditional transition from S0 and A0 to S1 are entangled with other states in some way. So everything is entangled. It basically means you cannot get hurt all the time. So it's a way to create an uncertainty set which is a bit more complicated than just a multiplication of uncertainty sets. And the theorem that is I want to present is that if you want to solve the conditional value at risk at 1 over eta, so think about eta as the budget that you have, equals the worst possible reward of delta eta, and delta eta is exactly the same. So if you're going to solve this particular robust optimization problem, where not everything can happen at the same time, so things are entangled, that's exactly the same as solving the CVaR problem. And that's a special case of a much more general result, that states that essentially whenever you have a risk measure of a particular type, the definitions are less important, but for those of you who are in the know, that's has to be a convex coherent risk measure. There is an equivalent robust optimization problem. And in fact, the reverse is true too. So whenever there is a robust optimization problem of a particular type of uncertainty sets, which are either product set or sets that have this, can be created in a way which is multiplicative and additive. So it creates something like that. So they can be entangled, but not in a way which is too complicated. There is an equivalent risk measure that you can optimize. So when you ask me what should I do, should I solve a robust MDP or should I solve a risk aware measure? Well, it's whatever it's more convenient for you because you're doing the same. So I think that this is really the message that I wanted to bring. If time allows, I want to just touch upon two issues which I think are really important, and those are recent works. And that the first one is how to construct an uncertainty set, and the second one is how to adapt online. So let me start with the first one, and I'll propose a model. This is a very simple probabilistic model. Whenever I'm going to choose a policy, pi, so I sometimes fail to do that. So with a small probability alpha, somebody else is choosing pi for me, and let's call it pi prime. So this leads to the following architecture, which we call the action robust. In this case, it's GDPG. It's policy gradient based, but that's less important. And the idea is the following: there is you look for an optimal actor policy, and then there is an adversary. This ties back to robust optimization that is going to do the worst possible thing against you on a greedy level. And then you evaluate the joint policies. The policy with high probability, with probability 1 minus alpha, succeeds to choose what it wants. But with probability alpha, which is small, the adversary modifies it. And now you have a loop of training. So you train the actor, you train the adversary, and then you train the critic, and you work in a loop. And this idea is really how do I construct an uncertainty set? Because one of the major difficulties in robust optimization is that you need the uncertainty set to come from somewhere. But it's not really where. Maybe there is a very natural physical explanation, but maybe there is not. And what we show, and this is something that I just want to touch upon, is that this is a graph of performance. This is some robotic domain. It's less important, but we see that yellow is high and red is deep red is bad. And we look here at noise probability and relative mass. So think about this as a robot, and we change the relative mass with respect to what it was supposed to be. So we have to adapt. And now what we see is that if you're going to allow this model, you're going to get a better generalization, even if your problem has no noise in it. So basically, you're going to get better results, even if you don't have any noise. And this is what we see here, that this is a matrix of performance, noise probability versus relative mass. The 0.10 is the original value. So this is the original problem. And what we can see here is that you can get superior performance even in the original problem, not to mention when there is some additional noise added. So I don't think I have time to go into the constructing uncertainty set. It's a very interesting and very important topic, very much worth diving into, but I don't have the time for that. So I'll just conclude by saying that for me, reinforcement learning has changed from mostly algorithms to data, understanding the representation, and then taking care of the five principles of extended intelligence. And just to mention that as someone who worked on theory and practice, full autonomy is very far away. So we are very far from robots you can send and hope that they'll do something useful. And RL works best when you have high throughput control and a very stochastic environment or a very good simulator. But real world is neither, so there is still a lot of work to be done. So with that, I will conclude. Thank you for your time.
Thank you. That was very nice. I guess we have to start the other talk in a couple of minutes. There were some comments about connecting your, latter part of the discussion to GANs. Is that something you want to throw
Yes.
some light on?
So basically, it is GANs to the point where you can show that the two concepts are equivalent. I think for GANs, many of us feel that GANs are sort of black magic kind of thing. This is not black magic. Here, you basically construct an uncertainty set on adversary, and this gives you an explanation why GANs work in this particular case.
Okay, so thank you so much. This was very nice.
Thank you.